So we move on to combine vertical and horizontal alignment. So as far as we have discussed previously that for the highway alignment, the vertical curve and horizontal curve were treated differently. However, the combination of the vertical and horizontal curve is quite common in geometric design and often necessary. So an example to this is through mountainous terrain and freeway interchange ramp roadways, which typically have to make significant changes in direction and elevation over a relatively short distance. So as mentioned previously, the design of an alignment that consists of vertical and horizontal curve is a combination consists of two-dimensional alignment problems. So we have certain illustration for the process. So we have here an example for the combination of horizontal and vertical alignment. A two-lane highway, which has 12 feet lane, has posted speed limit of 50 miles per hour. And on one section has both horizontal and vertical curves as shown in the figure. A recent daytime crash, the driver traveling eastbound and striking a stationary roadway object, resulted in a fatality and a lawsuit alleging that the 50 mile per hour posted speed limit is an unsafe speed for the curves in question and was a major cause of the crash. Evaluate and comment on the roadway design. So for this one, we have the illustration. We have the plan view for the horizontal alignment, and we have also the profile view for our vertical alignment. So we have here the illustration. Of course, we have the parameters or the variables that is represented by variables present in our horizontal alignment and vertical alignment. So for our vertical alignment, so this is a sag vertical curve. So for this one, if we're going to have here, so for this problem, we have to compute for the value for our length of the curve denoted by L. So that will be the station of PT minus the station at PC. So the station at PT actually is given by the equivalent value here is 32 plus 75 subtracted by the station of PC, which has 16 plus 00. So simplifying, we got a value of 1,675 feet. So this was converted. The result here is in station, so convert that one. So we get a value of, actually the result here is 16 plus 75 station, or this will be equivalent to 1,675 feet. Now, from the equation R is equal to 180 L all over pi times delta. So we can have here, this is 180 multiplied to 1,675 divide to pi times our delta, which is 80. So this gives us a value of 1,198.65 feet. So we have now our R. So with our speed limit, so if we're going to have the speed limit of 50 miles per hour with A, our super elevation is 8%. So our design speed, we have speed limit, which is 50 miles per hour. And of course, our A, the super elevation is 8%. So therefore, we can rearrange our equation wherein we can make use of the value for our f sub s, which is equal to v squared all over g times r sub v. You have to take note that our r sub v actually is equal to, we have to take note that the vehicle is traveling in the middle of the inside lane. So meaning to say our r sub v will be equal to r minus half of the lane width. This is half of the lane width. So therefore, if we try to substitute, this is 1,000. We have computed this one, 1,199.63. Then minus the lane width is 12. So half of that is 6. It gives us 1,193.63 feet. So therefore, if we try to substitute, our f sub s now will be 50. Design speed is 50 times, convert that to feet per second. So our multiplier is 1.47 squared all over 32.2 times 1,192.65. So simplifying further, we have this is minus 0.08 and they've got 0.061. So therefore, the value for our FS is from table 3.5. From table 3.5, the maximum F sub S for 50 miles per hour is actually equal to 0.14. So since our 0.06 does not exceed 0.14, so this is this one 0.061 does not is less than 0.14, so it does not exceed the radius. It does not exceed 0.14, so the radius and super elevation therefore are sufficient or 50 miles per hour design. So for the site distance, the available ms is 18. So for our site distance, our ms is equal to actually to 18 plus this is plus 6 feet, which is the distance to the center of the eastbound lane, or that is 24. This will give us 24 feet. So if we're going now to compute for our SSD, the stopping site distance, so we have to make use of the equation SSD is equal to pi times r sub v all over 90 multiplied to cosine -1 quantity r sub v minus m sub s all over r sub v. So this gives us pi times 1,192.65 all over 90, then multiplied to cosine -1 times 1,192.65 minus 24 all over 1,192.65, and this will give us 479.3 feet. So therefore, from table 3.3 again, from table 3.1, sorry, the SSD for 50 miles per hour design speed is 425 feet. So therefore, this is the minimum requirement, 425 feet. So therefore, our SSD, which is equal to 479, this is the computed one, is sufficient since it is greater than 425 feet. This is sufficient for our design. So turning to the sag curve, the length of the curve, if we're going to have now the sag vertical curve, for the sag vertical curve, we have the length of the curve, which is equal to the station of PVT minus station of PVC, and this will be equal to 18 plus 80 minus our 14 plus 00. So this will give us actually equivalent to 480 feet. So we have now the value for the length of the curve for the sag vertical curve. So therefore, for our A, using our A, which is the difference in elevation, actually, so we make use of 6%. Using the 6%, we have our K, which is equal to L all over A. So this gives us 480 all over 6. Actually, K is the horizontal distance to make an effect of 1% on the slope, 1% change on the slope equal to 80. So therefore, from our table 3.3, from table 3.3, for the K value for a 50 mile per hour, K is equal to 96. So therefore, since the computed K, this one is less than the required K, which has 96. So this is the 50 mile per hour is insufficient. So this is insufficient for the sag vertical curve. So which means that this is insufficient. However, because the crash occurred in daylight and sight distance on sag vertical curves are governed by nighttime condition, this design does not contribute to the crash, because you have to take note that the crash occurred on daytime. However, for sag vertical curve, we have to consider the factor in the design for the sag vertical curve is during nighttime. Since it occurs, the incident, the crash occurred on daytime, so that means that the design for the sag vertical curve has nothing to do. It does not contribute. It did not contribute to the crash incident.